Okay, so in this question we have a gate AB. So this gate over here, we're told that it has a homogeneous mass of 180 kgs. We're told that it's 1.2 meters wide into the paper, and it's also hinged at A. We're also told that it's resting on a smooth bottom at point B, and all fluids are 20 degrees Celsius. So for our properties, we're going to use 20 degrees Celsius as our temperature, and then we're asked to calculate H. That will cause the reaction force at point B to be 0. Okay, so the first step is to obviously draw your free body diagram of the gate. So we have point A over here, and then we have point B over here. Okay, and then let me just move this down. On the left hand side we have glycerin, okay, and then on the right hand side of the gate we have water, okay, and then this is H, then this is 2 meters, okay. Then for AB, the gate, we have a reaction force. We're going to have reaction forces at A, and we're also going to have reaction forces at B, but we're told in the question to calculate the depth of water, so H of the water, that will cause the reaction forces at B to be 0. So basically, if you keep filling this section with water, you can kind of like imagine the water will like flow and try and push on the gate. It would keep pushing on the gate up until it like starts to open up, right? So we want to like determine the exact point where the gate itself is barely touching at point B. So initially at point B, you'd have a normal force. So you'd have a normal force at point B, but in this case, this normal force is equal to 0, right? Okay, and then we have a hinge, basically, at point A. So we only have reaction forces in the x and y direction. And for simplicity's sake, I'm going to define my axis system to be along the gate, right? So I'm going to call this my y direction. So this is going to be AY, and then this is going to be AX. Okay, so I'm basically defining my axis system like this, just to make things a bit easier. Okay, and then another thing we're going to have is the weight of the gate. So we're told that the mass is 180 kilograms, and that will act at the center of mass, which is basically at the center of the gate, I guess, right? And then another thing we're going to have is the center of pressure. So this fluid over here is pushing on the gate. This one is also pushing on the gate. Okay, but you'll remember that, well, hopefully you do remember, or you do know this, but let's say that we have a little block, and this block is fully submerged in water. Okay, so from our previous examples and stuff and previous questions we've done in class, we'll know that the pressure at a specific point, so if I call this point A, so the pressure at A is just equal to the density of the fluid, so whatever fluid this is, times G times the height, right? And the height is the difference in height between the top of the fluid to the point that we want to calculate at. So it's this distance here, let's call that h. Okay, and this is for gauge pressure. So gauge pressure means that you're not considering atmospheric pressure. Okay, but that doesn't matter too much in this explanation. So we know that, okay, we can calculate the pressure at point A, right? What if I define a point over here and I'll call that point B? Okay, so then point B is going to have its own height, so let's call it HB. And then point A is also going to have its own height, let's call that HA. So pressure at A is equal to rho times G times HA. Pressure at B is equal to, again, rho times G, but now times HB. Okay, so the only difference now is the heights, basically. So the only thing that makes PB bigger or smaller than PA is the height, right? And yeah, since HA is bigger than HB, the pressure here at A is going to be a lot larger than pressure at B, right? And this is how the pressure gradient kind of develops. Just going to draw it better. So yeah, this is how the pressure gradient develops. So your pressure is a function of density, gravity, and height, right? But you'll notice that your density remains constant because we're assuming no temperature changes and all of that stuff. And then gravitational acceleration obviously remains constant. The only thing that's changing is your height, right? And yeah, this is basically the equation of a straight line. So you can think of it, your rho times G is your gradient. Gradient, T, that, and then your H is basically your variable that you're varying with, right? And you can see, although this is not the straightest line, but like you get a straight line that increases as your thingy increases, as your H increases. So your pressure, so each of these pressure vectors will get longer as your height increases, right? Yeah, I hope that kind of makes sense. So knowing this, we can represent pressure then as a linear distributed load, right? Which is basically what this whole thing is, right? It's just a distributed load. So knowing that, we can say, okay, I don't want to like I want to like simplify everything into a singular force, right? Just like we would with the distributed load. So all of this pressure will act, we can simplify it and say all of this pressure will act on a single point. So we'll call that P resultant, and all of it will act at a singular point, which is going to correspond to the centroid of this shape, right? And this point will define it as the center of pressure. So that's literally all the center of pressure is. It's basically the point at which all the pressure acts on a particular object, right? Yeah. So I hope that explanation kind of makes sense. And typically the center of pressure will be lower than the center of mass, provided that the whole object is submerged. So your center of mass would be somewhere in the middle, and then your center of pressure would be slightly lower. Quick reason for that is because your pressure increases as you go down, right? But your mass is considered uniform. So we assume the mass is uniform throughout the object. So the center of mass would be exactly at the center of the object, and then your pressure, it increases as you go down. So the center of it would kind of be, or like the centroid of it would kind of be in this lower region over here. Okay, I hope that makes sense. So knowing this, we can draw our center of pressure, right? And we know that we're going to have a resultant force from the glycerin, or rather a resultant pressure, which will cause a resultant force from the glycerin and also from the water as well. So we're going to have a force over here. So it's going to be the pressure Cg of glycerin times the area. Okay, so the resultant pressure that acts at the center of pressure. Let me repeat that sentence again. I don't know if I said it correctly. So the resultant pressure, right, that acts at the center of pressure is the pressure at the center of gravity of the object. So this PCG for glycerin is going to become, so let me just write it out, PCG glycerin is going to be equal to rho of glycerin times G times the height, right? But now your height is defined as the height from the top of the fluid to the to the center of mass of the object, right? So we're going to call this HCG. Okay. I know it's a bit convoluted. There's a whole confusing derivation about it, I guess. So yeah. But yeah, that's basically it. So the resultant pressure acts at the center of pressure, which is fine. We expect it to do so. But the resultant pressure, the magnitude of the resultant pressure is derived from the pressure that acts at the center of gravity, not at the center of pressure, if that makes sense. So in simple terms, when using rho GH to find your pressure, the H that you're going to use is the H from the surface to the center of mass of your object, right? Yeah, I hope that explanation kind of makes sense. And then you're going to have the pressure for water, PCG of water times the area, and you're also going to have nothing else, I guess. Okay, that's fine. And then we're told that the total length of this is 1, so this is going to be 0.5 meters. And then another thing we need to find is the distance between the center of pressure and the center of mass. So we're going to call that YCP. Okay. Cool. So what we're going to do to find H is we're going to try and take sum of moments at A, right? So we're going to take sum of moments at A, and that's going to leave us with PCG times A, and then PCG of water times A, and then PCG of glycerin times A, multiplied by the respective momentums. And then we also have the weight over here, so we're going to have the weight multiplied by its momentum, and then in the end we're going to get a long equation, and we want that long equation to be in terms of H. Okay, so we already have an equation for PCG of glycerin, so let's try and get an equation for PCG of water. Okay, so PCG of water is just equal to the rho of water, so the density of water, times G times the H to the center of gravity, right? So it's not going to be this H, unfortunately. It's going to be the H to the center of gravity, okay? But we can say that H to the center of gravity for water, so HCG for water is equal to H, right? So this total distance over here minus, sorry, I forgot to put this angle, that was 60. So minus 0.5 sine 60. So if I draw the gate, right? So in the middle you have your center of mass, right? This is 0.5, this distance here, 0.5, this is 60, so the height over there is going to be 0.5 sine 60, and then we have this total height over here, and this is the height that we want, so I'm going to call this HCG, and then this is H. So in order to get HCG, we need to take this height, minus it, or subtract this height here, and then we'll be left with HCG. Okay. So yeah, that's basically where that comes from. And then we're going to get PCG of water is equal to rho of water times G times H minus 0.5 sine 60. Cool. So we got an expression for the pressure of water, and then we can do a similar thing for HCG for the glycerin. It's actually just going to be let me just write it out. It's going to be equal to rho of G times G times H of G, which is the height of the glycerin. Let me just write it here. H of G, which is the height of the glycerin, which is this 2 meters. And then we want the distance from the top surface to the center of mass, right? So in order to get that, we need to subtract whatever this distance is, which is 0.5 sine theta. So it's going to be hg of glycerin, which is equal to 2 minus 0.5 sine theta. Okay. And theta is 60 degrees. Yeah, so got a nice equation for the two pressures. Okay. And then the area that we're looking for is basically the area that the fluid is in contact with. So they give us the dimension into the page, which is 1.2. So if you were to draw this in 3D, would kind of look like this, right? And then the fluid is in contact with this hatched surface, then this is 1.2, and then this distance here is our 1 meter. So the hatched area is basically the area that we're looking for. So this area is equal to 1.2 times 1. Okay. Yeah, hopefully that makes sense and you understand where these equations come from and stuff. So yeah, let's do our sum of moments. So we're going to do sum of moments around point A, and that'll be equal to 0 because everything's in equilibrium. And then we're going to get I'm just going to write it in terms of the pressure. I'm not going to write that full long equation. So we're going to get PCG of the glycerin multiplied by the area. So this is basically converting the pressure to a force. And then times its momentum, which is going to be basically, let me redraw it. So you have A, B, center of pressure, center of gravity. This distance has 0.5, and then this distance has YCP. Okay, so that distance there. Cool. And then your pressure acts at that point there. So your momentum is going to be equal to 0.5 plus YCP. Okay. Yeah. So it's going to be 0.5 plus YCP. Okay. And it was pointing that way, so it's going to cause it to rotate counterclockwise. So it's a positive moment. Then we can do the pressure from the water. So you're going to have PCG of the water times the area, and then again the distance, the momentum is going to be 0.5 plus YCP. Okay, and then you're going to have the weight. So we want the component of the weight that's going to act in that direction, which is going to be W sine theta, or mg sine theta, since they gave us the mass and not the weight. So it's going to be mg sine theta, and then your momentum is just 0.5. Cool. So plus mg sine theta times our momentum, which is just going to be 0.5. Then all of that is equal to 0. Okay, so we've got our equation for our pressures over here, and these pressures just have H as an unknown. Sorry, that as an unknown. Hg we know, which is the 2 meters. G we know, obviously. And then rho g we can get from our textbook. Theta we know is 60. So yeah, the only thing that's missing is h, which is perfect. That's what we want. So h is just the thing which I'm solved for. Cool. Now we need to find ycp. So we can substitute these equations here for pressure, and then we'll get our h over here as an unknown. The thing we want to rewrite now is ycp. Okay, so ycp is a weird one. So ycp is equal to negative ixx sine theta divided by hcg times the area. Okay. Okay. Cool. So this is related to just the gate itself, or just the portion of the object that's submerged, right? So when we say HCG, the part that we're talking about is the distance or the height to the center of gravity. So from the topmost part of the object that is submerged to the center of gravity. So this would be HCG. Okay. It's not this total height over here, and it's also not this height over here. So when dealing with ycp, you look at the object itself, if that makes sense. And also, if the object was slightly submerged, so if it was like that, then if I'm not mistaken, if I remember correctly, your center of gravity would be the center of gravity of this portion over here. So from the submerged portion, if that makes sense. So your center of gravity would be slightly lower than the actual center of gravity of the object, and then your hcg would be that distance there. Okay, cool. Yeah, so our hcg is this value here, because the entire thing is submerged. And then the area would be the area from before. So again, if I draw it in 3D, it's going to be this area here. Okay, so this is 1.2, that's 1. So your area is 1.2 times 1. And then your moment of inertia is going to be this 1.2. So the formula for area of inertia is 1/12 times b h cubed, right? The base, or b, is going to be this 1.2. So it's the dimension that goes into the page. And then the h is going to be the 1. So it's basically the length or the height of the object. Okay, so this is going to become 1/12 times 1.2 times 1 cubed. Okay, and then substituting all of those values, you'll be able to compute ycp. And then in the end, you'll get you'll be able to substitute your value that you get into here. Then yeah, you can simplify the equation and solve for h. So the only term, I guess, that will have h would be this term over here, if I'm not mistaken. Yeah, I hope that makes sense.